some news in quantum this week. I don't know if anybody saw the CHIPS announcement on Monday. It likely has a big impact. I think it's like $50+ billion. And we're talking about semiconductors, potentially spin qubits, but I think additionally other technologies as well. And I think it was called the Frontier Act before. So it's likely going to help, they say, keep a lot of the production of computers inside the US, or at least the research of it. And I'll post that in the chat as well. And then, so we got Ron. So Ron's gonna be a special speaker next week. And then Anna, let me know if you need anything. Presentation you should have access to. Okay, so besides the news with the chip stuff, anything else come to your mind, Anna, as we're prepping here?
Well, I just want to mention the medical applications of quantum. I didn't know there were so many, but Kevin provided a PDF with a bibliography. And I uploaded it to the cloud and posted a link in the comments for this event.
I appreciate it. So what Anna's talking about is between 2020 and this year, 2022, is there's been a number of research papers that have worked on, basically their analysis, methods, frameworks. Now the problem is the hardware has not been awesome these, past couple of years. And the hope is that we'll, learn and grow from these other papers. And I think Anna said she was going to post something on these, but we're talking dementia, we're talking COVID, EEGs, brain data. So again, the results aren't what people are looking for, and that's why we haven't heard about in the news. But it's very interesting that there has been such. I think the biggest kind of recent one is the IBM and Amgen. It's an IEEE, and it's on rheumatoid arthritis. So they say, their methods, and of course their conclusion is that our results are as good or better than conventional, which isn't the most promising, but the work is being done in quantum and medical. Okay. So I'm posting in the link. So this is that's a big link there. I'll just post the YouTube video. So you could listen to this afterwards, but there's, like I said, it's the Frontier Act. I don't know, let's see here. So, and, this is Chuck Schumer, who has been a big proponent for quantum in New York. So we're talking like global foundries, the whole kind of thing. Huh. And again, Anna, if you need anything from me, let me know.
Nope.
Okay, it looks like I have access to this link now. And then, do you want to talk a little bit about what you'll be talking about tonight?
Yeah, I'm going to be talking about quantum pseudo-telepathy. And what that is there are these cooperative games where you have two players and they need to cooperate in order to win, but they're not allowed to communicate. So they can't win 100% of the time. But if they have entangled quantum computers, even if they're not communicating, they could be on different galaxies. Nevertheless, they're able to win every time. And I'm going to go through the way they do that is when it's their turn to move, they ask their quantum computer what move to make. And the quantum computer performs a measurement on the quantum state and tells them what to do. And then it's the other player's turn to move. And because the two computers are entangled, the first player's move, color Alice, affects the state that Bob's computer, the second player's computer, sees. And so Bob's move is, it's as if Alice and Bob were communicating, even though they're not. And I'm going to talk about just how the computer actually performs that operation. And I'm going to walk through it in detail. It's quite simple. It involves multiplying 1 times 1 and 0 times 1, things like that.
Appreciate everybody coming on. Oh, we've got Dan Pompa returning too. It's always good to see previous special speakers. And then, so again, Ron will be presenting in a couple weeks here too. If anybody, especially for me, it looks like it's going more medical these next upcoming weeks. If you know anybody with medical and quantum, definitely let me know. Okay, anything you need from me on my end, Anna?
Nope. Just I need to be able to share my screen.
Should be. Yeah, it should be.
Yep. Shall I start?
Yeah, I don't think we see it, but I have it enabled. There we go. Okay. And then, were you able to share, Anna?
Yeah. So here's the game. It's played on a 3x3 grid like a TAC2 board. And Alice puts down, she fills in a row. The referee tells her whether to fill in row 1, row 2, or row 3. Then Bob fills in a column. And again, the referee tells him whether to fill in column 1, column 2, or column 3. And the rule is that Alice has to put down an even number of -1s. And Bob has to put down an odd number of -1s. Now, when Alice fills in a row and Bob fills in a column, there's going to be one square where the row and the column intersect. And if Alice and Bob both put down the same number, such as -1 or +1, then they win. But if their numbers are different, they lose. Without quantum computers, there's no strategy that is guaranteed to win, because they meet before the game starts and they agree on the strategy. For example, Alice might say, well, if I get row 1, I'm going to put down -1, -1, and +1. And if I get row 2, I'm going to put down all 1s. And if I get row 3, I'm going to put down 1, -1, and -1. That's just an example of a strategy. There are many different strategies they could choose. And Bob announces his strategy the same way. The thing is, there's no strategy that will allow them to win in all 9 cases, all 9 ways the referee can choose the columns, and I'll show you why.
So I saw more people hop on here. Go ahead, Anna.
So these are Alice's strategies, these 3 rows. And for Alice, this 3rd square has to be +1 because she has to put down an even number of -1s. And in this case, the only choice is to put down no -1s at all. These columns are Bob's strategy. Bob has to put down an odd number of -1s. So Alice would have to put down a 1 here, and Bob would have to put down a -1. Well, that's a conflict. They lose. Are there any questions about why Alice and Bob can't win without a quantum computer? They can't win every time.
Yeah, and go ahead and raise your hand, and then I'll unmute you. I think the biggest thing Anna said is without quantum computers, there's no strategy to win. If there's nobody, maybe you could kind of talk about that a little bit more.
Well, there's a strategy that will let them win most times. Like in this case, if the referee tells Alice to fill the first column and Bob to fill the first column, then they both have a 1 right here, so they win. Likewise, if the referee gives Bob column row 2, or gives Alice row 2, then they win. But if the referee gives both Alice and Bob, gives Alice row 3 and Bob column 3, then they have a conflict. Alice has to put down a +1 and Bob has to put down a -1. So they lose. They lose 1 time out of 9. Is everybody okay with that?
Yeah, and Ron in the chat, he says it's a lovely binary problem with symmetry. The pattern constraints are similar to barcodes.
Well, it's not quite symmetric because Alice's rules are different from Bob's. Well, yeah. Bob has to put down an even number of -1s. Alice has to put down an odd number of -1s.
Appreciate the comment. Any other comments? Could I unmute Ron, Anna?
Yes, you can unmute anyone. Just be prepared if it's a bomber to eject them from the room, which you do from the 3 dots next to their participant.
Go ahead, Ron. And then if not, does anybody else have any other questions right now for Anna? If not, you could go ahead, Anna.
So this is an example of one game. Alice's row, Bob's column. And this is just what I showed you before, that they can't win every time. So when Alice and Bob meet, they have to entangle their quantum computers. So they're basically preparing a 6-qubit state. I'm sorry, yes. This is the quantum mechanical formalism that is the state. And I got this right out of the Wikipedia article on quantum pseudo-telepathy. This circle with a cross in it represents what's called a tensor product. On the left, you have Alice's state, and on the right, you have Bob's state. And these letters, the I, the SZ, the SX, and the SY, are what are called Pauli matrices, named after the physicist Wolfgang Pauli, one of the pioneers of quantum mechanics. So this is what the matrix looks like at a high level. And I just used some software I had written to generate the matrix. And this is what it looks like. So it's all ones and minus ones, which makes the math very simple, and we're going to be able to walk through it. So it's all about eigenvectors and eigenvalues. This right here represents the first square in the first row. And this is the measurement operator that the quantum computer, Alice's quantum computer, uses. And when a quantum computer performs a measurement, they get a state vector out. And since it's a 2-qubit state, the state vector has 4 components. So if you multiply the measurement matrix, this right here, times the state vector, this is what you get. This matrix times this vector. Now, the way matrix multiplication works is you multiply the row of the matrix, you take its dot product with the column, which is right here. And so you multiply the numbers pairwise. You have 1 times 0, 0 times 1, 0 times 0, and 0 times 0. And you add those 4 products together and you get 0. Similarly, for the second row, you have 0 times 0, minus 1 times 1, 0 times 0, 0 times 0. And if you add those products together, you get minus 1. For the third row, you get 0, and the fourth row, you get 0. So the product is 0, minus 1, 0, 0, which is the negative of what we started with. And so what this says is that the quantum computer can tell Alice to play a minus 1 because it's negative A. Alice's computer could also pick plus 1. Well, we're still on minus 1. So there are 4 possible quantum states that can exist in Alice's computer. I've labeled them A, B, C, and D. The 2 eigenvectors, A and B, the vectors we just saw, their sum, A plus B, and their difference, A minus B. In every case, if you multiply the matrix of the first square times that vector, you get back the negative of the vector. And that says that Alice's first move could be -1. So there are 4 possible states after Alice's computer picks -1, A, B, C, and D. Are there any questions or comments?
Any questions? Let me know. There's a question. How does this differ from a free and or variable leading matrix formula?
I'm not sure what a variable leading matrix formula is. Could you explain?
So Ms. Chara, you can come on or type it in the chat. And then if not, if anybody else has a question, you can raise your hand or put it in the chat.
Is this microphone working for me?
Yes, go ahead, Ron.
Yeah, so Anna, when you said she can, the computer will tell her to pick a plus or -1, are you talking about for the first cell?
Yes.
Okay.
Awesome. And then Ms. Chara? Then if not, any other questions? You could probably go ahead, Anna.
Okay, so there are 4 possible states in Alice's computer, but only 2 of them are going to survive, and I'll show you why. In a moment. But Alice's computer could have picked a +1. These are the eigenvectors for +1. If you multiply the matrix of the first square times the vector E, right here, then you get back the vector E again. So that's 1 times E. It hasn't been changed to -E. So that says that Alice's computer could have picked +1 for the first square, for her first move. And there are 4 possible states, the 2 eigenvectors, their sum, and their difference. Now we're looking at the second square, and we're assuming that Alice's computer picked -1 for the first square. Here's the matrix for the second square. This is called an observable, and it represents a measurement. So if you multiply the matrix times the first state, you get back the first state. If you multiply the matrix times the second state, you get back minus the second state. So what that says is that Alice's computer could have picked either 1 or -1 for the second square. The states C and D don't work. If you multiply the matrix times the state, you don't get back minus the state, and you don't get back the state itself. You get back something different. So those states die. And what that says is the only possible state after Alice's computer picks a -1 followed by a +1 is A. And the only possible state after Alice's computer picks a -1 and a -1 is B. Are there any questions or comments?
Any questions? And then, Ms. Char, if your mic is working. Okay, you can probably continue.
Okay, so suppose Alice's computer picked -1 for the first square and +1 for the second square. The rule is Alice has to pick an even number of -1s. So I put it out to the group. What will the computer pick for the third square?
-1.
Absolutely. And if Alice's computer picks a -1 and a -1 for the first two squares, then what will it pick for the third square?
Any guesses?
1.
It has a finger up, +1, and that's right.
Very good.
So Alice's computer could have given her either of two legal moves, assuming that she started with -1. Now for the third square, and this is just a verification, we already know what the third square is going to be. But if you multiply the matrix times the third square, in the case where the first square is -1 and the second square is +1, you multiply the matrix, it says equals -1 right here. That should actually be -a. So that says that the third square is -1. That is, Alice's computer played -1 in the first square, +1 in the second square, and -1 in the third square. This is an even number of -1s. Likewise, if the computer played -1 in the first square and -1 in the second square, then it must play a +1 in the third square. And this is an even number of -1s. Are there any comments?
Any comments?
Okay. Now we go to Bob's computer. And remember what has happened. Alice's computer performed a measurement. This modified the entangled state of the two computers, even though they're on distant galaxies. This is what bothered Albert Einstein. You have what looks like instantaneous communication, faster than the speed of light. It's not really. And the reasons are subtle and difficult to explain. But Alice's computer modified the quantum state, and Bob's computer feels that action. So let's assume the referee told Bob to fill the first column. So again, this is the matrix for the first square of the first row and the first column. So the eigenvectors are the same. The two vectors that when multiplied by the matrix give you a negative result. So Bob can put down a -1 in the first square. And there are four possible states. The two we started with, their sum and their difference. So there are four possible states of Bob's computer after it picks -1 for the first square. But only two of those states will survive, as I will demonstrate. Now we move on to the second square in Bob's column, column 1. This is the matrix. If we give it state A, we don't get back a multiple of state A. We don't get back -A, and we don't get back A itself. So that doesn't work. B doesn't work. But if we take state C, then we get back C. which is 1 times c, right? Anything times 1 is that thing itself. So if Bob's computer played -1 in the first square, it can play +1 in the second square. Now, remember the rules of the game. Bob has to put down an odd number of -1s. So if there's a -1 in the first square and a +1 in the second square, what has to go in the third square? Ron's got a finger up, +1, that's right. And here we just verify it. We multiply the matrix for the third square times the state, and we get back 1 times the state. We get back the state itself. So Bob's computer picked a +1 for the third square. Now, if Bob's computer had played -1 and +1, then the states would be different, and it would have to play +1 for the third square. Again, this is an odd number of -1s. You multiply the matrix, you get minus the state. So that says the computer picks -1. That is, if it picked -1 and then -1, then for the third square, it has to pick another -1, an odd number of -1s, 3 of them. Are there any comments?
Yeah, Iman, go ahead, Iman.
Yeah, I think I've actually do this before, Anna, but why, you've got the 4 A, B, C, and D, and then you've got C is the sum of A and B, and D is the difference between A and B. Why is that? What's the logic there?
Why do we take the sum and difference?
Yeah.
Well, because if you have 2 vectors that when the matrix multiplies them, you get back a certain eigenvalue. Then if you add those 2 vectors together, then the result, and you multiply the matrix times the result, you get the same eigenvector. So the sum of eigenvalue, so the sum of 2 eigenvectors is itself also an eigenvector. This is because it's linear algebra. Linearity, meaning if you add 2 things together and then multiply, it's the same as if you multiplied first and then added them together. Does that help?
Yeah, it does. Yeah, it does. Thank you, Anna.
Sure, great question.
Any other questions?
So that's how Bob's computer picks a move for Bob. So I'm going to summarize it. There's 1 state for each legal move, and it's an eigenvector of all 3 squares in the row or column. The quantum computer uses the eigenvalues to generate a move. For the first square, there are 4 possible states. For a -1 move, only 2 of those states will survive. And for a +1 move, only 2 of those states will survive. Finally, you have the third square. So basically, this is a gauntlet. The state has to run a gauntlet. It has to pass through all 3 squares. And only one of the, actually you start off with 8 states, only one of them actually survives all 3 squares. And that's the move that the computer picks. And the same thing happens for the columns. Are there any questions or comments?
Hey, so Iman, you can come on, or when you say quantum computer, you mean qubit?
No,
Yeah. Anna, you always say quantum computer, but when they're entangled, it's the qubits that's entangled, isn't it?
Well, the quantum computers have a state, and the states of the two computers are entangled.
Yeah, but I'm merely saying, isn't, just to get the nomenclature right, isn't it qubit, not quantum computer? It's the qubit.
But it's
That's
the
it.
qubits that are in the quantum computer.
Yeah, you can't entangle two quantum computers. You have to entangle two qubits. Is I guess what I'm saying. It's just I find that a little bit I have found that confusing, and I've always assumed you meant qubit.
Well,
Am I being pedantic here?
I think the two computers are entangled. Each computer has a quantum state, and the quantum states of the two computers are entangled. Entanglement is really a property of a quantum state of qubits. Well, yes. No, actually, I stand corrected. It's the qubits that are entangled, not the computers.
Yeah, it's just it might confuse others. I knew what you meant. But yeah, fair comment. Thanks, Anna.
Hey, Anna, could you briefly go over the rules of the game again? Alice and Bob can prepare ahead of time for the game.
Yes, they can prepare their computers.
Okay, so
and entangle the qubits.
Alice prepares two or three qubits into an entangled state, and then she sends one to Bob, or sends two to Bob.
Let's see. There are I believe there are 4 qubits, but Alice's qubits get entangled with Bob's qubits before the game starts.
Right, but Alice originally prepares the qubits and then gives some to Bob.
Well, Alice and Bob prepare their qubits jointly, I would say.
Okay. And so this set of qubits that are prepared and correlated somehow, you have to do that before every instance of the game.
Yes.
Okay, so they by instance I mean they get one gets a row, one gets a column. They pick their numbers and they win or lose, and then they start over by creating new qubits.
They have to come together, set up their computers again, start over from scratch.
Okay. All right. Thanks. That's I just wanted to get that clear in my head. Thanks.
Yeah, it's the referee that brings in the random element to it. It's the referee that says your states are going to go into row 1, 2, or 3, and that's why you can't just place it where you want.
Yes.
Right, but again, you one instance of the game is just really the referee gives out 2 random pieces of information. The game is played, and then those qubits need to be everything's over with. You got to go back to the beginning and prepare a new set of qubits for the next game.
Yep.
Okay.
Yeah,
absolutely.
All right, gotcha.
So I've implemented this in software using my proprietary quantum simulation library, which is called QANA. And I'm going to demonstrate. So this is the board before the first play. Then the referee gives, it says blue, but that's really Alice. So in this case, the referee told Alice to fill in row 3. Then the referee told Bob to fill in column 2. And as you can see, let me bring up my annotation here. In the overlapping square, they agree. They both put 1. Now I go through all 9 cases. 3 referee choices for Alice, 3 referee choices for Bob. And as you can see, in every case, the overlapping square agrees between the 2 players, and they do satisfy the rules. For example, here, the row has an even number of -1s. It has 0 -1s. And the column has 1 -1, which is an odd number. So as you can see, they win in all 9 cases.
Any other questions for the speaker?
Yeah, I mean, it's more a comment. I mean, that is amazing. It's amazing that you've concocted this program that proves it wins 9 out of 9. Yet it's logically impossible to win 9 out of 9. But I don't know whether we want to bring contextuality into this at this stage, but I still can't understand how you win 9 out of 9. Can you explain it in layman's terms, Anna?
Well, it's the entanglement. Entanglement produces a correlation. This isn't exactly in layman's terms, but what Wikipedia says is that the entanglement produces a structure on the joint probability of their moves, produces enough structure that there's a correlation between Alice's moves and Bob's moves as a result of the entanglement.
Yeah, amazing. It'd be interesting to think if there's a practical application for this.
I haven't thought about that.
Yeah,
Well,
you could make millions of dollars.
Iman, you took the thought right out of my head. Isn't some of this technology the basis for quantum key exchange?
I think entanglement is very definitely involved in quantum.
Yeah, entanglement is, but this is more contextuality than entanglement. I'd be amazed if the military aren't using this amazing thing, because I hear what you're saying, Anna, but it's somehow more than entanglement going on.
Well, it could have a military application. Supposing you have the Army and the Navy and they need to cooperate to win the battle, but maybe their communication is limited, like Alice and Bob can't communicate. Maybe they can use entanglement to bring about some cooperation, even though the communication is limited.
So
Yeah.
does the game scale to 5 by 5,
No.
7 by 7, 9 by 9?
The Wikipedia article answers that question, I believe, but I don't remember what they said.
Yeah, no, the answer is no. Although I'm almost sure it doesn't scale. It has to be.
Wouldn't it just be a matter of engaging more qubits?
I know there are some cases that don't work.
Okay.
I don't know if it's 5 by 5 or which.
Yeah, I remember reading that too. It had something to do with the Hilbert space of being 4.
Just to reiterate the rules again, so Alice goes first, and Alice has to pick a odd number of minus ones?
Even.
Alice has to pick an even number of minus
Okay,
ones.
all right, so that could be 0 or 2
Yep.
minus ones, right? Okay, so would there be an well, I guess there wouldn't be an optimization there, but do you really need to do a quantum check on the third square?
No.
If you, yeah, okay. Because
That was verification. I just verified that the third square gives the right answer. Well, the quantum computer, let's see, the quantum computer would not have to perform the third measurement because it has the results of the second measurement.
right, once you have the first two squares, you can always compute the third.
Or Alice and Bob could compute the third. The quantum computer would only have to give them the first two.
Gotcha.
I believe. That sounds right. I'm going to show you my code, and that'll complete the presentation. So these are the basic matrices. They're 2x2 matrices invented by the quantum pioneers in 1931. This is how this is Python code. This is the 3x3 grid, this grid right here. So for instance, I have identity here. This is I. This takes a quantum state and gives you back the same state. This is sigma z right here, which is right here in the formula. And likewise for the second row and the third row. Now, one thing I haven't gone over is the initial state. Alice and Bob have to set up their computers in the initial state. So that's an excerpt from my code. This is going to be a product. It's not really a product yet. So if you want to participate, my website is quantumwithanna.com, and you can see how to get involved, how to support my project, our project. The last thing I want to do is give a shout out to my patrons who make this work possible. Well, my partners, Bruce Lang and Frank Stowicki, and my patrons, Barry Bird, Eamon Darcy, David Dosher, who's here tonight, Laura Hees, a VIP patron, Professor Richard Johnston, Sammy Kankar, Michael Kanovitz, Daniel Nickel, attorney, Jesse Parker, Jay-Z, Hiru Sechibuki, Ed Simon, Karen Slazak, also a VIP patron, William Slater, and Carrie Stratton, a VIP patron. And that is all I have, unless there are questions or comments.
Yeah, go ahead, Tim.
Yes, I just wanted to make sure that the only information that the referee gives to Anna is the row she uses, and then the only information that the referee gives to Bob is the column that he uses.
Absolutely. So that's
Okay.
classical information.
Okay, and then, so what is the information that Alice gives to Bob?
After the game starts, there's no communication.
Way to go, Anna. You put Alice out of work.
Can I ask you a question?
Sure.
Anna, your investigation, by the way, the work you have done on this is just Absolutely unbelievable. Have you done all this yourself, or has someone done a program previously?
No, I wrote the code myself.
I know you did. It's fantastic. Now, I think you should be speaking to Caltech and Google AI, who started this off with the zeros and ones. And I don't think they've got to where you've got to.
Well, they announced that there was a quantum strategy for winning the game, but when you and I contacted them and asked them what the strategy was, they never answered.
Well, that's not 100% true. You remember that little video they've done, which is the quantum strategy, but it doesn't make sense.
No, it's garbled.
Yeah, so worse than the fact that they just haven't got back is the fact that what they have presented is, well, I'm not saying it's not right, it could be in a different way, but they should know what you're doing and they should be interested in talking to you.
Well,
You should tell them you should tell them you've written the program that solves the Perez moment.
I only have, the only option I can think of is to contact, who's the world's leading quantum computing expert at Caltech?
Yeah.
Scott Aronson, are you thinking?
Oh,
No,
Presco?
Scott Aronson's in Texas.
Oh,
Yeah, John
okay.
Presco.
Yeah, John Presco. I could send him an
Contact
email.
him. Yeah,
Okay,
send him 100 emails.
I'll send him one tonight. Maybe I can find him on LinkedIn.
Yeah, the chances of it responding are slim. But just for the benefit of the group here, what Anna has achieved is mind-blowing. And John Prescott would be very interested in what you've done, I'm sure.
He could
But
do
again,
it
well done.
sleep, though.
Yeah, sorry.
He could do it in his sleep.
Oh, don't be so sure. Yeah, look, he probably could. Look, he's fantastic, as we know.
He knows
But
entanglement. He knows entanglement inside and out, forwards and
look,
backwards.
yeah, I mean, obviously, I mean, the work he's done with the Bell's inequality thing and all of that, it is amazing. But I still say this is more than just entanglement. This is the contextuality, Anna.
Well, what is contextuality, Iman?
Well, the contextuality is where a qubit, the properties of that qubit, like let's say spin, it depends on the context that you measure it. So when you, in our game, or the Perez moment, when you measure it as a column with the other two observables in that column, when you measure it that way, it gives a different solution to when you measure it in the row. Because the context is different. And that's what Perez Merman and John Bell came up with. They wrote that, the 3x3 matrix that they wrote proved that a subatomic particle, you can't define the property. So there's no hidden variable. They're fundamentally, as Einstein said, they're fundamentally different depending on how you measure them. If you measure them in the row, they equal this. If you measure them in the column, they equal that. That's the difference here. It's a lot more than just entanglement.
If you multiply the moves together by rows, you get +1. If you multiply them together by columns, you get -1. So it depends on the context.
Yeah.
So Anna, the algorithm that you're using that you coded, you could port that to Circ or Qiskit. And
Yes, I think so.
okay, and then my other question, I think, I don't know if you mentioned it tonight, I think you mentioned previously that you wrote your own tensor product routine. Is that correct?
Well, I actually use a library function for the Kronecker product from the SciPy scientific computing library.
Okay, so that probably just actually links through to NumPy, the NumPy Kronecker. Okay.
Well, I don't think NumPy has Kronecker products.
Oh, I'm pretty sure it does. It's in the linear algebra module. It's called cron, and it does a tensor matrix. But I could have swore you said that you wrote your own tensor generator, which would be a great exercise in learning how tensors
I wrote
multiply.
it first, and then I found out there was a library package, so I replaced it with what was in the
Gotcha.
library. There are
Sure.
3 Wikipedia articles I used for this. The one on the Kronecker product, the one on quantum pseudo-telepathy, the pairs Mermin square, and one on complete set of commuting observables. That told me about taking the sums and differences of the vectors to get the new eigenvectors.
Very cool.
Brilliant.
Awesome. Is there anybody that we haven't heard from that would like to ask questions either in the chat or you can unmute yourself? There's a number of people returning. Thanks everybody for returning. Dave, Carlos, just, Austin. There's a lot of people that have been on before.
Yeah, it's thanks, Kevin, for mentioning. I'm just catching up, so I've been quiet. I'm fascinated with what I'm hearing here. Sounds like some sort of holy grail has been put together by combining 3 Wikipedia articles, which is really something. And given how I forgot the name here. I think it was Ron was going on about it, this is fascinating. So, could I just get those 3 Wikipedia articles again that Anna, that you used? You mentioned commuting observables, and there are 2 others.
Complete set of commuting observables, Kronecker product, and quantum pseudo-telepathy. And between the 3 of them, it's the foundation for everything I presented tonight.
And you mentioned chronic product?
Kronecker,
Chronic.
Kronecker.
Okay, very good. Yeah, like when we build on that from the past and are able to put things together, then wonderful things show up. What occurred to me here is a pet theory I have about observation. We have the double slit experiment, and it is said that there needs to be an observation. What I think that you're describing here is the nature of the observation is important, and it was Enon, you were making those statements. The nature of the observation, or the context of the observation. So what you have created in terms of row-wise and column-wise, which changes the context, the application here is really your point of view. So it's the point of view of the observer which may cause a manifestation, which goes beyond the double slit experiment, and may explain actually what the relevance is, or provide a definition for what the observer has to be. And it shows that the observer may have a variable component to it. So you've, from my amateur point of view here, you've provided the next milestone in understanding the nature of quantum. Oh, sorry. You're on mute.
Thank you. And again, my website is quantumwithanna.com.
How are you doing on time, Anna?
I'm good.
Okay. Any other last questions for the speaker? And then, so make sure to check out her meetup. It's heavily attended. I put it in the chat there too. I think Anna may have done it as well. And any other last remarks, Anna?
I really enjoyed your participation. This has been a lot of fun.
Yeah, we appreciate it too. So I think it was kind of highlighted by Iman. You might be onto something. So it's always a good feeling. Yeah, I appreciate everybody coming on. This is episode 43 with Anna Naden. And have a good rest of your night and have a good rest of your weeks. Take care. Goodbye.